Another op-amp application is the analog-to-digital converter. Shown here in this figure is an analog converter, which is basically a mixed signal device where we have an analog input and a digital output, where B1, B2, B3, and B4 are digital outputs consisting of one of two values, either a 1 or a 0. B1 is the most significant bit and B4 is the least significant bit. Again, the output bits can only have 1 to 2 values, a high, a 1, or a low 0. And the code is used by these bits to represent the analog input, and it basically depends on the architecture of the ADC. So here we have a 4-bit digital output, and it's associated with it is a fixed reference point voltage, which we'll see in the next figure. So here's an implementation, and this is a analog to digital converter. In fact, this is a flash analog to digital converter, or ADC, and it's flash because everything operates simultaneously, and we'll discuss this in detail. So this is our flash analog to digital converter. Again, as mentioned earlier, we have a V reference point and our 4-bit digital output. Here we have 4 op-amps configured as a comparator. We have our voltage source being compared with these reference values, these different reference values. This is a voltage divider circuit, and we note that very little current is flowing into the non-inverting inputs of each of these comparators. So here again we have an analog input Vs sub t feeding into this flash ADC with a 4-bit digital output with a fixed reference voltage V reference. Again, the output bits can have 1 or 2 values, a high, a 1, or a 0. So B1, B2, B3, and B4 can either have a high or a low value. Again, it either rails to the plus VCC or the minus VCC. Now the reference voltage is applied to this voltage divider string, in which we have successive taps of this voltage divider to supply as a reference voltage to each of the inverting inputs of the comparators. Now these reference voltages are all different, and each is larger than the reference voltage of the comparator immediately below it. So if this was 10 volts, this point, since we have 5 resistors using a voltage divider, this would be 1/5 the voltage, or 2 volts. This would be 4 volts, 6 volts, and 8 volts. Alright, so that's our reference points if V reference is 10 volts. So these are different reference voltage as it compares with Vs. Now the output of any one comparator is high when the analog input exceeds its applied reference voltage. Otherwise it's just a low, 0. So let's take this example. Let's say our V reference is less than 0.2 V reference and is greater than 0. When it's below this, that means Vs is below this reference point of 0.2, 0.4, 0.6, and 0.8, and therefore the output voltages is corresponding all 0. Now if Vs is greater than 0.2, then B4 would have an output reference of 1. I mean a digital output of 1, and the rest would be 0. Now if Vs is greater than 0.4 times the V reference volts, alright, then B3 and B4 would have 1 and 1, and B1 and B2 would be 0 since it's below 0.6 and 0.8 times the reference voltages respectively. So if V reference is between 0.4 and 0.6 of the reference voltage, then again Vs would be at the output would have B3 equal to 1 and B4 equal to 1. Now once it's greater than 0.6 and below 0.8, then B2, B3, and B4 would all be 1. And you can see the pattern. It's almost acting like a thermometer. It's just rising as Vs rises, and therefore as Vs gets to greater than 0.8, then all of these outputs will be 1, as shown here. So that's how this flash converter works. Okay, again, because the reason why it's flash, because it takes the comparator output and it operates in parallel, and the conversion takes place almost instantaneously. Now, we mentioned earlier that the circuit divides the input amplitude range into 5 bins and converts each bin into a unique 4-bit code. Now that the full-scale input range is the voltage range over which the input amplitude falls within one of these bins, between 0 to V reference in this example. Now this range can obviously be increased by increasing the reference voltage. So I can, earlier I mentioned this was 10, we can raise it to 20. But the price of doing so is reduced resolution, which is defined as the largest input voltage change that falls within one bin. So in this case it would be 0.2 V reference in this example. Now the resolution can be improved by really expanding the voltage divider and basically include more resistors and more comparators, adding more comparators. In fact, some integrated circuit flash converters can have as many as 256 comparators. Now the patterns of ones and zeros shown in this table is called like a thermometer code, as I mentioned earlier, because the number of 1 increases monotonically as Vs increases, like the way the mercury column in a thermometer increases with temperature. The integrated flash converters have built-in decoders that convert this thermometer code into a standard binary code. The flash converter is by far the fastest analog-to-digital converter architecture. And that concludes this discussion. Okay, so let's take a look at an example now where the V reference is equal to 15 volts. And let's say our voltage is S is 1 volt. Now we note that because this is 15 volts, then V reference divided by 2 times 0.2 is 3 volts. Here this would be 6 volts. Here this would be 9 volts. And here would be 12 volts. Now with V reference of 1 volt, it's below this 3 volt reference, so therefore all these bits would be 0. So for Vs, therefore the output would be 0, 0, 0, and 0 for B1, B2, B3, and B4. Now let's see if Vs is equal to 2 volts. Again, since it's below 3 volts, the digital outputs would be 0, 0, 0, and 0. Let's say its Vs now is 5 volts. So 5 volts is greater than 3 volts, so B4 would be 1, but it's still below 6 volts. So B3 would be 0, as well as B1 and B2. Let's say Vs is equal to 10 volts. Well, it's greater than 3 volts, 6 volts, and 9 volts, but it's below 12 volts. So this one would be 0, 1, 1, 1. And then finally, if Vs is 15 volts, then it's greater than 12, 9, 6, and 3. So therefore all of these would be 1. Hopefully this example illustrates how the flash converter works. This flash analog to digital operates. So the more op amps you have, the better the resolution. So now this concludes this discussion and this example of analog to digital converters in terms of op amp applications.